everyone, and welcome to our week on molecules. This is a really short section, and I purposefully did that so that you have extra time for your voice threads. I want you guys to be really successful on those and focus mostly on that. Okay, well, let's get started on our one and only lecture for the molecules section. So I want you to think about what it means to manipulate molecules and design drugs. You have a feel for what medications are in general anyway, and most of you have tried Tylenol or ibuprofen at some point in your life. But what about prescription medications? Is our society becoming dependent on prescription drugs? And we're starting to see this more and more with opioid addiction. People go get a surgery and then they come back and they can't get off the medication, their painkillers, and then they have to go on other medications so that they don't have to keep taking the painkiller medicine. So it's becoming an increasingly big problem. And how harmful are illicit drugs? There's actually been some studies that show that some of the drugs that we think are harmful, these women take them when they're pregnant and the babies actually come out okay. They have higher chances of getting addicted to drugs later on in life. But what we used to think that, opioids, for example, we used to think that they're really terrible for the fetuses. We're finding that, most of these babies are coming out okay. It's just they're addicted when they're born. That's the only problem. And then herbal remedies. Are they safer than synthetic? Not necessarily. And how are effective drugs designed? So let's start with just a simple beginning. This is just one example of many, right? We have so many medications out there. But back in the olden days, people used to chew the bark from the white willow tree. I should say willow tree here. And it would reduce fever, and it would reduce pain. It would be anti-inflammatory, and it was seen as a wonder drug, So these people would use it. And eventually chemists got involved, and they were able to determine that it's salicin in the willow bark that was allowing people to feel better. And here is the structure of salicin. And what happens when people would chew it and eat it, it would become salicylic acid. And this worked fine, but it had some downsides to it. So the chemists actually eventually converted salicylic acid into aspirin. So here is a salicylic acid again, and this is what you would normally get in nature. But salicylic acid has this group right here where you see OH. This hydrogen would come off, and it would make the stomach acidic, and it would cause heartburn or too much acid in the stomach. And so this was one of the negative side effects. So what people found, this chemist found that if they reacted salicylic acid with acetic anhydride, that this group here, this blue functional group, would actually attach to where the hydrogen used to be on salicylic acid. So you can see that where the O here, that blue functional group, now is attached to O. And you'd also get acetic acid on the other side. And what would happen is this would block the hydrogen. Basically, it would block that acidic effect in the stomach, so people can eat it, and eventually you can get into the bloodstream, but not cause the acid like it normally would have. Okay, and this functional group, this blue functional group, is an ester. We call this esterification because we put an ester group on the molecule. There are still some possible side effects with aspirin, this new form here that was synthetically derived from the willow bark. It can still cause heartburn, it can cause nausea. It can cause Ray's syndrome, which is a very serious syndrome. It's one of the reasons why you say you're not supposed to give aspirin to young children. It can cause actually permanent damage. So they say you shouldn't give it to young children, and that's why. ringing in the ears. It can cause rash, itch, and shortness of breath. Now the question for you is, would this drug make it through FDA scrutiny today with all of these terrible side effects? Well, yeah, it probably would. Pretty much every medication out there has some kind of side effect. So this section about molecules is actually a little bit of an introduction to organic chemistry. Organic chemistry is really the study of carbon compounds. Currently, there are over 12 million known organic compounds. And why is carbon the focus here? Why is organic chemistry so focused on carbon? Well, first of all, life is typically made up of a lot of carbon. But not only that, carbon is a special molecule, and it has the ability to bond in multiple ways. If you look at this first carbon here, it's bound to 4 single bonds. 1, 2, 3, 4. Okay, this is typical. Carbon needs 4 bonds. If you look to the next molecule, you have 2 carbons here, and really it's still bound to 4 things. Look, you have 4 bindings, right? So you have 1, 2, 3, 4. So a double bond here, so it makes it 4. Same thing here. You can have a triple bond with carbon. Okay. You can have carbon with 2 double bonds to still give it 4. All right, or you can have an O with a carbon or a nitrogen triple bound to the carbon. Right, so it has just so many ways you can bind it. And to get started, I'm going to go over really briefly some ways you can represent molecular structures. One way is the structural formula that you see on the left. This one just shows you carbon, hydrogen, all the bonds. This one you're familiar with is like your Lewis structures. Then you have ball and stick model, right? Everything looks like a ball and you have sticks in between. And then you have space filling model. And this one's actually more accurate to what the molecule probably looks like. So it's just showing where all the electrons and parts of the atom would most likely be. You also have, in this slide, just to show you, you have different ways that molecules can form with the same structure. So if you notice, there's 1, 2, 3, 4 carbons here. Notice that's N-butane. Notice the one down below, isobutane. You have 1, 2, 3, 4. 4 carbons again. You have the same hydrogens on both of them. It's the same chemical formula. Those are isomers. But the structural formula is different. Notice that this one, this isobutane, is more compact. It's just everything is more compact looking. So it's going to have different properties. So it has the same chemical formula. When it has a different structure, it has different chemical properties. So probably the easiest way to represent molecules is with the line angle drawings. So you see the structure on the left has all the atoms in it, and that's just a lot of work to draw. If you're a chemist, you have lots of molecules you're working with. So it's just easier if you can represent it with lines. And that's exactly what this is. So if you ever see a structure with just lines, it's understood that at each vertex there's a carbon. That's just conventional. It's always going to be carbon. If it's not carbon, you're going to write the atom down there. And it's understood that those are all carbons. So just to show you what that looked like, there's all your carbons. So at each vertex there's a carbon. And don't forget that each carbon has 4 bonds. So if I were to look at this carbon at the end, it already has 1 bond to this other carbon. So I need 3 more bonds. Conventionally, it's just you don't write them, but it's known if there's nothing else written there, it's going to be a hydrogen. There we go. So this one has 3 more hydrogens bound to it. So there's 1, 2, 3, 4 bonds. This carbon here at this vertex in the center, it has bound to 1, 2, 3 carbons. So you just know it's going to be bound to another hydrogen. And you can do this for the entire molecule. Same thing here. You look at cyclopentane, right? All the carbons are bound here. You can actually just draw it as a shape, as a pentagon. This is a nice table that just shows you what other molecular representations look with the line angle drawings. Right here was the N-butane from the earlier slide. Very simple drawing here now. I love it. So much easier to do. The isobutane, you can see how it looks compact now. I kept saying it was compact earlier. Maybe it's hard to tell. But in this representation, it's much more easier to see that. Same thing, N-hexane, you know, it's just 1, 2, 3, 4, 5, 6 carbons. And the cyclohexane is 6 carbons, but they're all connected to each other. One of the most important compounds that you will see represented is a benzene ring. So if you look on the left, this is what a benzene ring looks like. You see a double bond, single bond, double bond, single bond, double bond, single bond, and all the hydrogens here. So each carbon should have 4 bonds. 1, 2, 3, 4. This would be, again, painful to draw every single time. So instead, you drop all the hydrogens and you just draw the carbons as vertexes. Okay, so see the double bonds here. Well, we know with all these double bonds, we can have resonance. This was from earlier, we talked about resonance. Since there's resonance, another way of drawing benzene is just with a circle in the middle, and that just indicates that these double bonds, you know, they're not exactly double bonds, right? Because the bonds are shifting between everything. So instead, you can just draw a circle. And another way to represent it would be space filling model, but again, that would be too hard to draw, really. That's a computer calculation or a computer generated model. We went over functional groups already, but I just wanted to show you this table. It's really nice. But different functional groups, they're really important when designing drugs. Different arrangements of functional groups impart characteristics, different characteristics, and that's in terms of physical and chemical properties. So for example, your hydroxyl group here, this would be ethanol, like alcohol. This is just an OH group. You can have dimethyl ether, right? This one's dimethyl ether with an ether group, which is COC, or aldehyde, which is C double bonded to OH, or a ketone, right, where you have the double bond C and O, but then you have 2 carbons down below. Carboxylic acid is one of the big ones in this section that we're going to talk about, and in the next section as well. And ester, that's when we talk about esterification. That's because we attach this ester group. Amine is just nitrogen with 2 hydrogens. And finally, an amide, okay, which looks like an amine with a carbon and a double bond O. So here is an example of an esterification or an ester formation. So you have this group here, right, on the left-hand side. All right, so you have an OH group, and you have another molecule on your right-hand side with an OH group. So this OH and that H actually combine and make water. And then you're left with an ester group on the right-hand side. This is actually a really simple technique that we even do in just general organic chemistry here at CI in the labs. So here's our aspirin molecule, and I want to go over the functional groups. So already one, I hope you can recognize very fast, that would be your benzene ring. 2, you have that double bond COOH, that would be your carboxylic acid. And finally, 3, you have your ester group. So you have 3 different groups here in your aspirin. I don't expect you to memorize these groups, but you should be able to identify them looking up at a table. And finally, we're going to talk about polar molecules. So you already know water is polar. You have this partial negative, partial positives. Your alcohol groups, your hydroxyl groups are also very similar. So here's a hydroxyl group. You have a partial negative and a partial positive on your hydrogen. Your carboxylic acid also are polar. So your O group, your O oxygens are partially negative and the hydrogen's partially positive. This is again important. This is also important in terms of designing drugs. The way they interact with the body depends on if they're partially negative or partially positive. So that also determines which kind of functional group you might wish to choose as a scientist. So for example, here's pseudoephedrine. It's a medication. In its free base form, it would look like this with an amine group. And it's not as stable in this form. And so what happens, chemists try to turn forms like this into a salt. And you could do this using HCl. These two would react. And what happens, you would get a pseudoephedrine hydrochloride salt. And this actually looks a lot like, by the way, sodium chloride. You have the chloride, so this is a salt. Sodium chloride is a salt. So here's your salt. So instead of this being sodium, you have pseudoephedrine portion with the chloride. This is the ideal form because salts have an increased water solubility. They have lower vapor, which is great, so they're more stable, they don't smell, they last longer, and they have higher melting and higher boiling points, so they have a longer shelf life as well. And finally, just to give you an idea of how a lot of the drugs do work, it's just with the lock and key model. It's a very simple form, but it's just a nice way. So the cells have these receptor sites, and each cell has a specific lock, right? And these drugs, they act as the key. So these drugs can actually go and they can fit into the receptor. And this will actually open the pathway for whatever natural substrate that's in your body to interact in your cells. So it can actually allow for the natural stuff in your body to occur more efficiently or faster. So that is actually a very powerful way that drugs work. All right, well, that is it for this week. I hope you enjoy the readings, and I will see you guys next week. Bye-bye.